Hi, in this video we will review two more differentiation rules, product and quotient rules, and we will do some examples for these rules. Okay, let us start right away with the rules. What does these ones say? So we're assuming that two functions are differentiable, and then when you multiply them, you will get another differentiable function. The derivative of this is not product of the derivatives, but it's Leibniz rule or the product rule, which is derivative of first one times second one, and then first one itself times the derivative of the second one. And then we have quotient rule. Let me write the rule here, and this says something about the derivative of the quotient of two differentiable functions at points where the denominator is not zero in the neighborhood of that point. Okay, this is differentiable and the derivative is another quotient. The denominator is the denominator of the function squared. The numerator is the derivative of first function times second minus the derivative of the numerator. So the numerator itself times the derivative of the denominator. Derivative of numerator times denominator minus numerator itself times the derivative of the denominator. Well, seeing a proof of these guys are nice. You have to do once in your life at least. I will do the product rule here. You can check the book for the quotient rule. So two functions multiplied, we want to find the derivative. Okay, well, at point say A, then the derivative is same thing as the rate of change, instantaneous rate of change. So that means that we have to find limit of this guy as x goes to A. Yeah. So here, the trick is this. You see that to generate the derivative of f, you need fx minus fa. Yes, but we have either fx times gx or fa times ga. Well, what we do is we add or subtract fa, well, and I multiply gx such that I can factor out that gx. Well, I added a new term to numerator, subtracted. Now I have to add the same term just to cancel out and don't have any changes in the numerator, and then write the last term in the numerator, which is here. I write there x minus a as x approaches to a. Now we can separate the denominator. You see this is 1, this is 2. We can write it as limit of sums of two things, but you will see that they have limits, so I can separate the limits, use the product law, and write two limits, sums of two limits, fa gx minus fa ga, x minus a, x approaches to a. Here, you can factor out gx. In the other one, you can factor out fa. So this is limit of x approaches to a, fx minus fa over x minus a times gx. Well, we can apply product law here for the limits, and you will see that the limit of each one exists for a good reason, and then you can write it. In the second one, however, f at a is a number, so you can factor out, and then by constant multiple law, it comes out of the limit. So this is gx minus ga over x minus a. Well, we have a limit here. This limit is nothing but f prime at a. Here, well, the second part is fa, and that is g prime at a. How about this piece here? Limit of gx as x approaches to a. You know that g is a differentiable at x equal to a. As a result of that, g is a continuous. Means what? Means that the limit of gx as x approaches to a is the same thing as the value of the function. And this is what we were looking for. This is product rule. Derivative of first one times second one plus first one itself times the derivative of the second one. Other than well, these small tricks here, you have to be able to use these rules. So you have to get them so well so that you differentiate each time. You can do it easily, all the work. You can work with these guys. So these are the tools you have, the toolbox of differentiation. For example, here we have two functions. The derivative will be the product of these guys. So this times the other one, we have to use product rule. So it will be derivative of first one times second one plus the first one itself times the derivative of the second one. This is a polynomial. Apply the sum, differences, constant, multiple, and power rule. You get 2x plus 3 times e to the power x plus x squared plus 3x minus 1. Derivative of e to the power x is just e to the power x itself. Now you can factor out e to the power x. This is 2x plus 3 plus x squared plus 3x minus 1. You can simplify a little bit more, yes. You can write x squared plus 5x plus 2, everything multiplied to e to the power x. I won't do that step. You can do it yourself. Okay. The second one is the quotient of two functions. So we have to use the quotient rule. Derivative of the numerator times the denominator minus the numerator itself times the derivative of the denominator. And then the denominator squared. This will give us derivative of t minus 4 is 1. So the first piece will be just 1 times t squared plus 1. The second piece is t minus 4 is just that. And derivative of t to the power 4 is 4t to the power 3. Derivative of 1 is 0. And this is t4 plus 1 squared. You can work a little bit more, simplify the numerator. I will leave it for you, this one. Okay. At first sight, you see, well, this is product two things. Then let's apply product rule. But with the rules I have covered so far, I don't know what is derivative of e to the power negative x. We will learn it very soon. But I cannot differentiate. I don't want to use that rule. What I want you to see is that, well, we can change this one to this and get rid of that negative sign. Then g prime of x is derivative of the numerator times denominator minus numerator times the derivative of the denominator, and then denominator is squared. Derivative of root x, it is 1 over 2 root x. See, x root x is x to the power half. Apply the power rule, you'll get this. E to the power x minus root x. Well, this is what? Derivative of e to the power x is e to the power x. I don't have. Derivative of e to the power x squared is e to the power 2x. Now we can factor out e to the power x in the numerator. We get 1 over 2 root x minus root x. And in the denominator we have this. This cancels with that, and we have 1 over 2 root x minus root x. Denominator is e to the power x. That's That's the derivative. A little bit different form. We have a function f in terms of g, and then we know that g is differentiable at 0, and we also know what is the value of g. Okay, so there is something missing here. F prime is equal to 0 and g at 0 is equal to 2. Then find g prime at 0. Okay, well, I know that the derivative of f can be found in terms of derivative of g, because you see this is derivative of numerator times denominator minus the numerator itself times the derivative of the denominator over denominator squared. Well, if you do apply the differentiation rule for this piece, this is product of two functions. Derivative of first one is 1 times e to the power x plus first one itself times derivative of e to the power x is e to the power x. This times g at x minus x plus 1 e to the power x g prime x. Then the denominator is this guy. Well, what do we know? We know that f prime, if you plug in x equal to 0, we have f prime at 0 equals to e to the power 0 plus 0 plus 1 e to the power 0, g at 0 minus 0 plus 1 e to the power 0, and g prime at 0. And this is g0 squared. Well, we know that f prime at 0 is 3. And we know that g itself at 0 is 2. So we have 2 squared there. This guy here gives us 2. So 1 plus 1 times g at 0 is 2 itself. Minus this guy is 1 times g prime at 0. You see, everything is just number, and we have an equality. We can solve it for g prime at 0 equals, well, solve it for that. So this will be 12, and then g prime is equal to 12 minus 4, which is 8, and then g prime at 0 is negative 8. This is, well, just a little bit twist on quotient and product. Oh, well, and we have another example where we have two functions. We don't know what are these functions. What we know is that there's a table of values for this function, and we want to find derivative of, for example, f over g at 0. So we are trying to find h prime. So h prime can be written in terms of f prime derivative of numerator times denominator minus fx times g prime of x over gx squared. This is for all differentiable points, this will happen. In particular, if x is equal to 0, h prime at 0 is going to be equal to f prime at 0, g at 0, minus f at 0, g prime at 0, over g at 0 squared. And this is f prime at 0. You see this guy, this is 2. G at 0, this is g at 0 is negative 2, minus f at 0, the function itself at 0 is 1, and g prime at 0 is 3, over g at 0 is a negative this squared. And that gives us what is h prime at 0, which is negative 4 minus 7 over, Yes, negative 7 over 4. How about this other one? Well, let's just differentiate first. H prime at x is going to be derivative of the numerator, which using the product, the constant multiple rule, you have this, times a denominator minus, why this is going that way, minus the numerator itself times the derivative of denominator. This is sums of two things, so you will have sums of their derivatives. Then gx plus fx squared. Well, at 1, so h prime at 1 then is 3f prime at 1, g at 1, f at 1, minus 3f at 1, g prime at 1, plus f prime at 1. And then this is g at 1 plus f at 1 squared. Well, I need that table, so let me just take it from there. Paste, I will put it here. Okay, so the values I will pick from there one by one. F prime at 1 is 0. Okay, this is nice. Everything else there will be 0. But let me just put the values. F at 1 is 2, G at 1 is 1, minus 3 times. F at 1 is 2, G prime at 1 is 1 itself, plus F prime at 1 is 0. And G at 1 is 1 plus 2 squared. And this gives us what? This whole piece will be 0. This is going to be negative 6 over 3 squared is 9. So simplify, you get negative 2 over 3. Well, you have to know the product and quotient rule, and you have to be able to use it when it is needed.